Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're solving examples of shear in built-up beams. The next example is a problem from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. I chose this example because it is a design-like problem where we have to look at several different considerations that may govern the design. The problem statement reads, a box beam is fabricated from two plywood webs, these are the plywood webs, that are secured to dimension lumber boards, these are the lumber boards, at the top and bottom flanges. The lumber has an allowable bending stress of 1500 psi. That implies that we need to check the bending stress in the lumber. The plywood has an allowable shear stress of 300 psi. That implies that we need to check shear in the plywood webs. And then finally, the 3/8 inch diameter bolts have an allowable shear stress of 6000 psi and are spaced at intervals of 9 inches. And this shows the longitudinal direction and the spacing of the bolts. This implies that we need to check shear across the connection interface. Support A is pinned and support C is a roller. So what we're asked to do is determine the maximum load P that can be applied to the beam at midspan. Let's say find P allowable, and it's a point load, presumably in kips. And then we're to report the actual bending stress in the lumber, shear stress in the plywood, and average shear stress in the bolts at the load due to the load that we determined in Part A. So one of those three considerations will control the actual value of P, but then we have to go back and report the stresses in the other parts of the beam. So let's talk through how to set this problem up, and then we'll go back and solve. And the first thing we need to do, if we're going to check bending stress and we're going to check shear stress, we need to find the maximum shear in the beam and we need to find the maximum bending moment in the beam. Since this is one of the common cases that we should be able to sketch very quickly, I've already laid it out for us. Point load P in the middle of the beam causes reactions of P over 2 at the supports, causes a shear force diagram that jumps up to P over 2, jumps down to negative P over 2 at the middle, and back up at the right support. So the maximum shear in the beam, max V, is equal to P over 2. And then the bending moment diagram starts from 0, increases linearly, has a maximum value equal to the area under the shear diagram, P over 2 times L over 2, which is PL over 4, and then similarly comes back down to 0 on the other side. The important thing to note here is that our max moment is equal to PL over 4, occurs in the middle of the beam. Okay, so we have, as we mentioned before, we have three criteria for design. Let's lay those out a little bit more specifically. The first one, bending stresses. We'll say criterion 1 is the bending stress in the lumber. Bending stress sigma in the lumber. Okay, we can solve for maximum bending stress. Sigma max equals MC over I, and we'll take the maximum moment in the beam, so we'll write this in terms of P, is PL over 4 times C over I. Let's take this equation and solve for P, which gives us an allowable load, P allowable, equals 4I over LC times the allowable stress in the lumber. That's the first consideration. Second consideration, I'll say criterion 2, is the shear stress in the plywood. Shear stress in the plywood. For this we can use our equation tau max equals VQ over IT, and we'll go ahead and substitute the maximum shear, which is P over 2 times Q over IT. Solve for P allowable. P allowable equals 2IT over Q times tau allowable. So that's our second consideration. Another important thing to recognize here is what area we need to use to calculate Q. Remember, the max shear in the plywood webs will occur at the neutral axis. So if we draw our section, sketch our section just real roughly, we want shear at this location right here at the neutral axis, so we want to consider the entire area above when we're evaluating Q. And that's going to be very distinct from what we do in the next criterion. The last criterion, as we discussed briefly before, is the shear stress in the bolts. Shear stress in the bolts. Okay? Shear stress in the bolt, tau bolt, is equal to the shear force in the bolt divided by the area of the bolt. So we can write the shear force in the bolt, because we're going to have to relate this to shear flow, equals tau in the bolt times area of the bolt. Now our shear flow capacity, if you will, is equal to the shear force in the bolt, V bolt, divided by S, the bolt spacing. And we're going to multiply that by 2 because we have 2 bolts across the connection interface, one on each side. So each of those can carry some of the shear. That doubles the amount of shear that can be carried. Let's write that as 2 tau bolt times A bolt divided by S. From a demand point of view, the shear flow is equal to VQ over I. So, and that we'll rewrite as P over 2 times Q over I. So the point load P on the beam is going to cause a shear flow equal to this value. What we need to do here is set these two equal to each other. P over 2 times Q over I equals 2 tau bolt times A bolt over S. We'll solve for P. P allowable equals 4 I tau bolt times A bolt over Q times S. This was our last criterion. As mentioned earlier, we're solving for shear in a different part of the section here. We're solving for the shear across the connection interface. So the area that we need to use to compute Q is going to be different in this case. This is a quick sketch of my section. We want shear across these interfaces right here. So the best area for us to consider would be the area of this inner lumbar flange. So this would be the area for Q for this problem. Okay, so now we've defined the 3 criteria that we need to check for the design and to determine the allowable load. We'll continue this problem in the next video.